Hello friends, welcome to GYAN. This is a control question. In this question we have given this differential equation where y is output and x is input. It is asking for the poles of the input. So we will use Laplace. So this differential equation in terms of Laplace I am writing. So this will be like s square ys plus 4ys is going to 6x of s. So s square plus 4ys is going to be equal to 6x of s, or the transfer function y of s upon x of s we will get as 6 upon s square plus 4. So the denominator is going to give us 4. So we will equate denominator equal to 0. So equating s square plus 4 equal to 0, we will get s square is equal to minus 4, which implies that s is going to equal to plus minus 2j. So this is our answer. In this question, we have given open loop transfer function g into h of s as k upon s plus a s minus b into s plus c. Now it is saying that the closed loop poles encirclement of 1 plus dshs is in counterclockwise direction, which implies that n encirclement of closed loop poles is going to be equal to 1. So it is asking that number of closed loop poles on the right hand side of S plane. So it is asking for the Z. As we know that by Nyquist stability criteria, n is equal to p minus z. Now we have given n equal to 1. Z we have to find. So this open loop transfer function, so poles of open p is nothing but poles of open loop transfer function. So from here this poles of open loop transfer function RHS of S plane. So from this open loop transfer function we can say that only one pole is on the right hand side of S plane. So P is going to be equal to 1. Now we have P and we have N, so we have to find Z, which implies that Z is going to be equal to P minus N. The Z is going to be equal to 1 minus 1. So encirclement about so the number of closed loop poles on the right hand side is going to be equal to 0. This is on the basis of Nyquist stability criteria. So we will get our answer as 0. Here we have given open loop transfer function g into h of s as s square plus s plus 1 upon s cube plus 2s square plus 2s plus k. So we have to find the value of k for which system become marginally stable. So here we will use Rao-Hurwitz criteria, which says 1 plus GSHS is equal to 0. First of all, we will find closed loop poles. So this is going to be 1 plus s square plus s plus 1 upon s cube plus 2s square plus 2s plus k equal to 0. Or we can say s cube plus 3s square plus 2s plus s 3s plus k plus 1 is going to be equal to 0. Now by using RH criteria, we will write s cube s square s to the power 1 and s to the power 0 So 1, 3, 3 and k plus 1. So s to the power 1 is going to be 9 minus k plus 1, and this is k plus 1. So for system to be marginally stable, the coefficient of s to the power 1, to find the value of k, we equate coefficient of s to the power 1 equal to 0. So this 9 minus k plus 1 is going to be equal to 0, which implies that k plus 1 is equal to 9, or we can say k equal to 9 minus 1, that is equal to 8. So our answer is going to be 8. In this question, we have given this diagram, we have given of output, input we have given, and open loop transfer function, as well as some feedback is given to us of a system. So we have to determine the order of the system and the stability of the system. So order represents highest power of closed loop poles. So first of all, we will find closed loop poles, 1 plus GHS. We will equate it to 0. Now, the closed loop transfer function of the system will look like CS by RS is going to be GH, that is 1 upon S plus 1 into 1 upon S square upon 1 plus 20 upon S plus 20 into 1 upon S plus 1 into S square. So this transfer function will look like S plus 20 upon S square S plus 20 into S plus 1 plus 20. This is the CS by RS. So this represents the closed loop poles, and highest power of this term will be the order of the system. So this will be, order of the system is going to be S square plus 20S plus S plus 20 plus 20 equal to 0, or we can say S to the power 4 plus 21 S cube plus 20 S square plus 20 equal to 0. So this closed loop poles has highest power 4. So order of the system is going to be 4. And now to check the stability and instability, we can use Routh-Hurwitz criteria. So by using Routh-Hurwitz criteria, the essential condition is that all the power of S must be present in the closed loop poles. So here we can say, for a system to be stable, the all power of S must be present. So here we can see that S to the power 4 is present, 2 is present, S to the power 0 is also present, but S to the power 1 is not there. So from this equation only we can say the system is unstable. So our option will be order 4 and system unstable. Here in this question, it is given that a stable LTI system is given, which have a single pole at P, and open loop transfer function of the system is given like this. Also given is DC gain of the system is equal to 5. So it is asking for the value of omega for which system gain become 1. So here we will use a gain margin and phase margin method. So first of all, we'll convert this open loop gain into time constant form to get the DC gain. So S square plus 100 upon S minus P. We'll write in terms of 1 plus S square by 100 100 I am taking common. Again I am taking minus p common, so it will become 1 minus s by p. So from here we can say that the open loop gain of the system, open loop gain, DC gain of the system is going to be equal to 100 by minus p, and DC gain of the system we have given is 5, which implies that p is going to be equal to minus 20. Now we will replace this p in this open loop transfer function and we will equate the gain of the system equal to 1. So how the system was going to look like? S squared plus 100 upon s minus minus 20, so this will become s plus 20. Now we will write in terms of omega, so it will become 100 minus omega square upon under root of omega square plus 20 square, and this gain of the system is given with is 1. So from here we will get our omega as 100 minus omega square whole square become equal to omega square plus 400. So this 10 to the power 4 plus omega to the power 4 minus 200 omega square equal to omega square plus 400. Will bring all these terms to this side. This will be omega to the power 4 minus 201 omega square plus 10 to the power 4 minus 400 equal to 0. So this will be omega to the power 4 minus 201 omega square plus 9600 equal to 0. Now we'll replace omega to the power 4 by omega square by a, which will implies that this equation will look like, so this equation will look like a square minus 201a plus 9600 equal to 0. And now we will find the roots of this equation. Sorry, it was not visible. So here we will solve this equation. We will get the two values of a, and is asking for the smallest value of omega. So the smallest value we will get from this term. So we will get our omega as 8.83 radian per second. Thank you.